think this will help you remember, but if you take this thing and move it around now, move it over here, move it over there. I'm not changing the shape of it, I'm just moving it around. What is that called? Well, transformation's even broader. It's any kind of change. Even if I did change the shape of it or the orientation or reflected it, that's a transformation. If I'm just sliding it around one way or the other way, it's called a translation, or sliding it. The mathematical word is translation. If the equation of this is y equals x squared, if I shift it up to, what's the equation of that? Y equals x squared plus 2. Where did my notebook go? So on here, I think I have, that's one of them for you here. Well, I got minus 4. If the equation of this is y equals x squared, if you take this and go down or up to, if I go up 2 here now, that's y equals x squared plus 2. Or if I go down, this is down 4 here, y equals x squared minus 4. Basically, you have this function, x squared. The function is squaring the number. Take an x value and square it. If I perform an operation outside of that function, after I apply that function, like minus 4 here, it's a vertical change. It takes all the y values and does that, or whatever, right? It moves them. If you have a point that is like 2 gives me 4 on the basic graph, the point 2, 4 is on the basic graph. If I do that to the function, what point is going to be on this graph that corresponds to this one? If 2, 4 was right here, where is it going to be now? Do you want me to show you and you'll see? If you move this down, what happens? Where's it going to be? I moved it down 4. Where is it? It's 0, right? Every point on the whole thing moves. So if 2, 4 was on that graph, 2 zeros on this graph, the y-coordinate changes. The y-coordinate is 4 or less. The x-coordinate didn't change. If you have a change outside of the function after you apply the function, like this, it changes y. Okay? Changes y. Okay, translates 4 down. If you make a change before this, let's think about this point right here still. Okay? We're going to think about this point, and if I can get rid of that yellow, just write it again, it's easier. If you make a change inside of the function, so here's my function, right? My eraser's not working very well. If I do this, as in if I make a change inside of that function, before I apply the function, if I put a minus 3 in here, what happens? You probably learned, well, when it looks like that, I do this on the graph. You might not have understood why. What happens? What did you learn last year happens when you have that minus in there? 3 to the right, right? And you probably thought at first, why when it's minus 3 does it go to the right, the positive direction? Take a look at this point here. When I want to get the y value from the x value, what do I get to go from there? What operation do I do to go from the y to the x, or x to the y? You square it, right? You square the number. This is square the number. If I want to still end up with a 4, this point I want a 4 there, what do I have to start with here if the first thing I'm going to do is subtract 3? If the first thing I'm going to do is subtract 3, and I want it to equal 4, I got to start with a 5, right? I have to start with something that's 3 larger, because the first thing I'm going to do is subtract 3. This is why this graph goes to the right, because when I subtract 3, it's like I'm taking 3 away from that point, then squaring it. It does the opposite of what you think. You can go through and fill in the blanks. I tend to go a little blank happy when I make fill in the blanks things. I put too many blanks. Like, I put so many blanks you can't figure out what it is, right? This one might be doable. I don't know. You can try for yourself. If you can't do any of the fill in the blanks, then, don't worry about it too much as long as you understand the concept. Now, the harder one was this. This is the harder one. The harder one was this. If you started with this, I'll try to draw it as nicely as I can. And then I'll see if this is going to work. So there's my parabola. Get rid of this. I don't need this right now. There, can you read that? What happens, the other thing you did here was you did this, right? You made it taller and you made it shorter. Notice that you might not have called it taller and shorter because it looked like it was getting wider and skinnier, but we were supposed to be looking at it as a vertical stretch or a vertical, well, I call it an expansion and compression. You know, I've been doing some writing of new math resources and stuff. In Alberta, they seem to not believe in the word expand and compress. I'm having no end of frustration with the fact that they call everything a stretch in Alberta in their math curriculum, but the stuff we're producing is for the whole West, and Alberta is kind of the bully of all the provinces. So we have to use the word stretch. If I said to you, stretch this graph vertically, what would you think in your mind? Like this, right? That's stretching it. Would you call this a stretch if I went down there like this? Is that stretching it? No. Guess what they call it in Alberta? That's a stretch. This is a stretch by 2, maybe. It's twice as tall. This is a stretch by 1/2. I've warned them that it's not a good idea, but they don't listen. I will call this a vertical expansion and this a vertical compression. Okay? Because that's what it is. When you look at it on the graphing software here, actually hold on to that for a second. You might have thought of it like this, right? When we do some other graphs, we're going to look at expanding, compressing horizontally as well. But for parabolas, you just looked vertically. And to be true for the functions we're looking at here, we're just going to look at vertically as well. So we're not going to think about horizontally yet. How did you get that to happen? If I wanted this to be twice as tall, as in if I wanted this point right here, let's put a point right there. If I wanted that point to be twice as high up, what value that sort of looks twice as far up? It's actually twice as tall, my point, but it's not really a point anymore. But what would I have to do? If the original one was y equals x squared, what's that new function? Y equals 2x squared. The value in front of the function, outside of the function, after you've applied the function, as in if you were using function notation, f of x, it's out here, not inside here. It's after you've applied the function. You've squared it, then you multiply by 2, it changes the y values. That point that I had before that was at 2, 4, where would it go? It's not at 2, 4 anymore, where is it? Is it going to change the x value or the y value? The y value. The y value is not going to be 4 anymore, it's going to be 8. It's going to be twice as much. I'm reminding you of all of that because we are going to need to look at it with exponential functions, like this. 2 to the x. That's one of the basic functions. The problem is this looks like a number and, well, it is a number, but it's part of the basic function. You're going to get confused, like what does that 2 do? You need to know what the basic function is and then start changing it around. If you know what happens with this function, I'm going to put brackets there so it's easier to see what's happening. If you know what things do to that function, you know what things do to this function. If you know that putting a minus 4 on the end of one of those, if you know that doing this makes it go, what did this do? Made it go down 4. If I put outside of this function here a minus 4 on the end, what does that do to this function? It's going to go down 4, right? If you go to this, not this, if you go to this, what's going on here now? There they are. If I am going to go, let's think about which one I used here. I did this, right? This is just going to shift that whole thing down 4 like that. Okay? If I put a minus 4 there. The entire graph looks the same shape and everything, but it's going to go down 4. Everything's going to go down 4. The problem is people make mistakes because of that y-intercept is not at 0. So you say, where is it? They'll always say, if you go down 4, it's at negative 4. Where did it actually go? The asymptote's at negative 4. Where's the y-intercept gone? 3, right? Because it started at 1. So this is what you have to pay attention with. That's why it's a bit harder. If you put a plus 4, it's up at there at 5. Okay? All right. If you now put the second possible thing here, if you know what happens when you put a number inside the function, if you put a minus 4 right here, what did that do to that function? It makes it go to the 4 to the right. How do I put something inside of this function? On the exponent, right? I have to put a minus 4 right here. If you wanted to, you could write it in calculator lingo, and then it would look like it's inside, 2 to the power of x minus 4, like that. Then it's clear that it's inside, not outside, right? That's going to shift it which way? That was what I was using the value of C for. If I do this, it looks like it's going vertically because there's no reference point for going horizontally here. This is another troubling thing for people. That green dot doesn't help. I should probably get rid of that green dot. Let's get rid of the green dot. Come on. It is having trouble. Well, because this computer doesn't ever, this program doesn't slide it sideways like that. Unfortunately, the way the shape is, it's hard to tell that it's going sideways. It is. Okay, my green dot's not turning off there, but whatever. All right? That's a horizontal translation. If you imagine a vertical line through the center, it's going to shift as well. If I put a 3 in front of this function, what's going to happen? It's going to get vertically expanded, right? Let's go back to the way it was here. Come on. This is really good. How about if I just put it back there myself? 0. Almost 0. If I change the number in front here, if I change this from a 1, is the y-intercept going to change? Is the y-intercept going to change? If I put a 2 in front of this, every y value changes, including the y-intercept. This is not like changing the base. Changing the base, the y-intercept doesn't move. Putting a number in front here, like this, 2.3 times 2 to the x, every value is 2.3 times bigger, or whatever this is, 7 times bigger, or 6 times bigger. If I put a 6 there, make it a nice number to work with, like 6. Try again, like 6. Too fine here. There. This is at 6, not 1. It's 6 times as high. Every other point's the same point. This point was at a half. Now it's there. All right? Every point is 6 times as high. You need to go through and work on that in all these cases. I've asked you, like, what happens when you change this to this? What happens when you change this to this? And so on. Then I'm actually asking you to do this here, and I don't want you to use a calculator for it. I gave you the dots that show the basic graph here. And you're going to do it by thinking about, well, what does this actually do to the graph? And every point on the whole thing moves. You can imagine where the asymptote goes. If you change the asymptote horizontally, does it change? Doesn't, right? That's why it was so hard to see the horizontal translations before. I put some little thought bubbles in here for you. There's lots of pages because everything takes up so much space. You're not using a calculator. Think about what changes the asymptotes, the domains, the ranges, all those transformations. And then we're going to kind of summarize this. You can try and summarize it yourself for what each of those do. But we can summarize it later as well. What we're doing today is you're going to spend a bit of time on that, and then I'm going to let you do this quiz that I've been